a little bit, complex, because in pre-calculus we use a whole lot more complex functions than we would have ever thought about using in Algebra 2. Now we have new vocabulary. We have zeros. Okay, zeros always correspond to the x-intercept, or a zero is when the function output is equal to 0. So once again, we're on the x-axis, so they can be called zero, roots, or they can be called the x-intercept. All three are interchangeable terms. All three correspond to where our function touches the x-axis. The next one is we have line symmetry. Line symmetry is where we're able to draw either a vertical line or a horizontal line and be able to replace and be able to cut our graph in half and then lay it on top of each other. If it's vertical, you're looking at like more of a parabola, whereas x squared. If it's horizontal line symmetry, in reality, that's not going to be a function, but it could still have horizontal line symmetry, like the graph of the square root of x has horizontal line symmetry. We're going to talk about point symmetry. Point symmetry is where you're able to rotate the graph about a point 180 degrees, and it maps directly on top of each other. Okay, line symmetry and point symmetry are also the determining factor of what makes a function even or odd. A function is even if it has symmetry about the y-axis, meaning that if we were to split it and fold over the y-axis, we would map on top of each other. Odd functions have point symmetry about the origin. Okay, once again, we'll talk about that. Even function, once again, has symmetry about the y-axis. Odd function has point symmetry about the origin, or the point 0, 0. The first thing that they're going to be asking you to do is to estimate function values, and we are using the graph specifically from this. Okay, the nice thing about graphing is that you can find answers pretty quick, but they're always an estimation. It's very hard to be exact with a graph. If we want to be truly, truly exact, we have to plug in values algebraically. Okay, that's really the only true way we get an exact answer when we're dealing with graphs. So it says advertising. The function f of x is equal to a negative 5x squared plus 50x. Approximates the profit of a toy company where x represents the marketing cost and f of x represents profit. So in a real world, they're trying to determine how much money they should spend on marketing. Okay, and you can see from our graph that we have a high point, so there's a possibility that we could spend too much on marketing and not enough on marketing. Okay, so our y value is the profit, the money we clear after expenses, and the x value is our marketing budget. How much do we spend? Okay, it says both costs and profits are measured in tens of thousands of dollars. Use the graph to estimate the profit when marketing costs are $30,000, and we want to confirm our estimate algebraically. So key things when you're estimating graphing, make sure you understand what's happening on the units. Okay, so you can see that they're both measured in tens of thousands. So when we're at the origin 0, 0, marketing budget 0, profit 0. If we go 1 unit to the right, most people would say that that's 1, but once again, we're in tens of thousands, so that's $10,000, 1 unit to the right of the origin. Then we go a second unit, that's $20,000, and then we go $30,000. Okay, so now working the same way going up, looks like they're counting by 25s. So if we go up, we have 25 times 10,000, which is 250,000. Then we have 500,000. Then we have 750,000, and then we have a million. 100 times 10,000 is equal to 1,000,000. Okay, so looking at this graph and using our units, it looks as if when we have $30,000, when we put in, oh, why are my markers always dead? You guys got to remind me to put caps on my markers. They're always dead.
There's a jar right there that's on the bookshelf.
What?
There's a jar markers on the bookshelf.
I know, but they don't have any black markers in there. I only like to write in black. So it looks at when this marker sucks too.
Mr. Ray, you push the button and change the side.
Oh, I did. Dang it. Thank you, Miss Archie. It looks as if when we were at 30,000 or we spent $30,000 on marketing, we made $1 million. Okay, and we can get that from the graph. So 30,000 is 3/10,000. The function value of x equals 3 appears to be about 110,000. So the total profit would be roughly 1 million. To confirm this, we have to do it algebraically. So to do it algebraically, the first step is we want to write what our equation is. Let's see if this works. There we go. F of x is equal to a negative 5x squared plus 50x. And we are to find f of 3. So once again, in this scenario, we want to actually plug it in to check algebraically. So I've written down my equation straight from the problem. And I am going to plug in 3 into my equation. Make sure they do. Okay, so here I have negative 5x squared. If I'm going to plug in, that's negative 5 times the quantity of 3 squared plus 50 times 3. So now using order of operations, 3 squared is 9 times 5 is a negative 45. Okay, plus 50 times 3, which is 150. So if I combine these, I would get f of 3 is equal to 105. Okay. Understand that if we were to put 105 as our answer, we would get that incorrect. Okay, that's because we had the units where they are tens of thousands. So this is 105 times 10,000, and that comes from the units of our graph. So that's going to be 105 with 4 zeros at the end of it. And if you look, I get 1,050,000 as my answer. So now we have to ask ourselves, is this really an appropriate answer? Is our estimation good? Okay. And the way that we verify that is it always helps to use the units. I don't like how you have to bounce back and forth because then the thing doesn't work. So to estimate that if this is a good one, you can see on the y side, they're counting by 25s, right? It goes up 1, that's 25, then 50, then 75, then 100. The next one is 125. Okay, so in this situation, we wanted to break it down. We're really like 0.5 off, which would make our estimate very reasonable. Okay, we're not exact because we're estimating, but we confirm it algebraically. So we plugged in 3 and we were able to get 105. But once again, we had to multiply it by 10,000 to get 1,050,000. And the estimate of $1 million is pretty reasonable. We're only $50,000 off. And we would put our algebraic answer. Okay, so when you're estimating these and they ask you to check it algebraically, you're going to have your graphic estimation answer, but then you're also going to have your answer when you check it algebraically onto your homework. Okay, both will be required. Oh. Okay, so here we go again. B, advertising. The function f of x is equal to a negative 5x squared plus 50x. Approximates the profit of the toy company, where X represents marketing costs and F of X represents profit. Both costs and profits are measured in tens of thousands. Now it says use the graph to estimate marketing costs when the profit is $1.25 million or $1,250,000. Then we can confirm this. Okay, so once again, we're going to use our graph. And here, instead of working from the X up, we're going to work from the Y down. So 1,250,000 would be right about here. So we're going to scroll to the right, and it looks like we hit that at the X value of 5. Okay, so what we're assuming is that when we spend $50,000 on marketing costs, our profit is equal to, where did I do that market? Is equal to 1.25. So, in order to check ourselves, we would have to set up our equation. Okay, and we can actually abbreviate our zeros so we don't have to deal with a ginormous number like 1.25 million. Okay, and once again, the way that we would check it is we would plug in our X value that we thought. So from the graph, I grabbed, it looked like that when I hit the X unit of 5, that's where I wanted to be. That was my magic number that made my Y value 125. So once again, we just double check it, plug it all in. So 5 squared is 25 times a negative 5 is a negative 125. Plus 50 times 5, which is 250. Negative 125 plus 250 is equal to 125, which is where I want to be. So that is an estimation that happened to turn out to be exact. And you'll find when you're estimating using graphing, it's so much easier when they actually intersect X and Y. Okay, if it's a little bit above the grid line for the X value or the Y value, we can be off by 50,000. But once again, we're estimating, so we just want to make sure that our graphs are reasonable. Get to the next one. We don't need to estimate it. Okay, any questions about how we're going to estimate using the graph? Got a pretty good idea, more or less. We're always going to estimate it graphically, but then we are going to verify it algebraically. Okay, so we're either going to plug it in and solve, which is the most popular way that we can do that. Okay, so the next thing that they're going to ask you to do on the homework, and could ask you to do it on like the SAT, it always helps to understand this, says use the graph of f to find the domain and range of the function. Once again, our domain is all of our x values. Okay, so if you want to make a note, just say your domain is x values. Okay, all the possible. Your range is your y values. Okay, and once again, it's all possible. When you're looking at a domain, there's two situations where you wouldn't encompass a number, okay, in the domain. That's when the function becomes undefined, which means we're dividing anything by 0. Okay, we don't want to plug in an x value that makes the denominator of our fraction a 0, because you cannot divide anything by 0. It's undefined. So that would eliminate an x value from your domain. Okay, the next thing, we are not going to be dealing with imaginary numbers. Okay, and imaginary numbers, once again, would be like 4i, or the even root of an odd number. Okay, the even root of an odd number gives you imaginary, it's not real, therefore we cannot encompass it into our domain. Other than that, most times our domain is all real numbers, unless it's cut off like this graph that we're going to have here. Okay, but key concepts, your domain is your x values, your range is your y values. It's mostly all numbers encompassed in the domain, unless it makes the function undefined, where we have a 0 in the denominator, and that's after we plug the x value in, or if it yields us an imaginary number. Okay, both of these situations would eliminate that or that possible x value from our domain. Okay, Rosalind, that's fine. I'm going to post the lecture. Glad you're here now. Just if you need to look at the lecture before you do your homework, it'll be posted as soon as I'm done. Okay, or as soon as I can get YouTube to work with me enough to get it uploaded. Okay, so here it wants us to use the graph to find our domain and range. Okay, key things when it's asking you to use a graph is you want to pay attention to make sure that the graph is wholly consistent. Sometimes they'll put a circle in there that shows it could be, it's what's known as a jump discontinuity. Okay, so we want to make sure our graph is continuous. And then the next thing we want to pay attention to is what's going on at the end here. You can see on this left side in quadrant 3, we have an arrow that continues to extend down. Okay, we have to assume that that continues and continues and continues, and it never ceases until we hit a negative infinity. Okay, but if you look at quadrant 4 off to your right-hand side, here we have the graph comes to a blunt stop. Okay, it doesn't go past that. That is the book telling you, or the graph telling you that, hey, this is the limit of the domain. So when we're looking at the domain here, it looks like if we go 1, 2, 3 units to the right, that's our high end. So our domain cannot be greater than 3, but 3 is encompassed because it has a colored in circle. Okay, now if we're looking at our negative side, even though that graph looks like it drops straight down, just understand it still extends to the left. In order to get this graph to go farther and farther down, we have to move farther and farther left on our x-axis. Once again, it has an arrow. We cannot assume, or we have to assume that graph is continuous and it stays going. Okay, we're not going to imagine that a jump discontinuity or discontinuity happens after or in an area where that's not shown on the graph. So the domain for this one, using interval notation, is a negative infinity to a positive 3. Okay, a negative infinity to a positive 3, which will be expressed just like this. Parenthesis, negative infinity, bracket around 3 to show that it is contained. Now we ask ourselves the same question. We have the range and we have a couple maximum values, okay, on our graph. If it looks, analyzing the graph, looking at the range now, you can see we have a couple high points that happen at the y value 2, and then our graph doesn't go above that. Okay, so those are going to be our maximum values. So those are going to be the end of our range. So they're going to be on the high side of our range. Parenthesis. And then looking as our graph goes very to the left. Oh, I forgot to share it. So once again, these are our high values. They happen at the y value of 2, and we don't extend higher than it at any point on the graph because we have to assume it stays that way. So we have 2 as a maximum value. Okay, and then our graph continues as we go farther left. It continues to a negative infinity. So our range is going to be negative infinity to 2. Our domain should be a negative infinity to 3. Once again, we graphed that just by looking at the equation or looking at the graph. They didn't give us an equation, so there's no way to check it algebraically. So for the domain, the dot at 3, negative 3 indicates that the domain of f ends at 3 and includes 3. The arrow on the left side indicates that the graph will continue without bound. So the domain of f is negative infinity to 3. That's interval notation here. Okay, interval notation here. In set builder notation, the domain is stated as x. X is less than or equal to 3, and x is an element of real numbers. In this case, interval notation is just fine. Okay, so the range, the graph does not extend above y equals 2, but f of x decreases without bound for smaller and smaller values of x. So the range of f, once again, is negative infinity to 2 with a bracket on 2 showing that it is included. On that one, I messed up my interval notation. And there would be your answer. Off to the next one. We got a multiple choice question. Should be quick, should be easy. We're looking at it. It says use the graph of x to find the domain and range of the function. Okay, this one's a little tricky. This one is a piecewise function. This is what's known as a piecewise function because it has the jumps here. It would be expressed as a jump discontinuity. Okay, so once again, we want to analyze and make sure that our individual parts are it's continuous where we actually have the graph, and then after the jump, we want to make sure that it's continuous here as well. So you can see our domain is 1, 2, 3. It's not inclusive of negative 3, but then it extends all the way to 1, and this point makes it a function to this point. Okay, so our domain looks like it's going to be negative 3, jump down once we hit 1, to a positive infinity because our graph continues to go without bound. Okay, so our domain is negative 3 to infinity. We have a bracket on negative 3 because it's not included. And then we want to look at our range. So we stay pretty consistent at 1, but then we go, we know we're not including negative 1, and then we're down to a negative infinity. So we want to find an interval notation that has us from negative infinity to a negative 1 with negative 1 out, not included, and then also has 1 within brackets. So looking at this one, I'm going to say that it's B because we have the open boundary at negative 3 for the domain that corresponds to this circle. And then the positive infinity just means that we extend farther and farther to the right because domain is our x values. And then if we're looking at our range, this negative infinity to a negative 1 open here is talking about this portion of the graph. Okay, working from negative infinity going down all the way up to the negative 1. And then the bracket portion of 1 is talking about this. And you might look at it and say, D could be a possible answer, but since we have an open circle on negative 3, they have a bracket on negative 3, that would show that negative 3 is included. So if D was the answer, we would need to have a closed circle on -3 here. So you can see they kind of get tricky with you. They like to do open circles to more or less confuse you, but if you just analyze the parts individually, it's a pretty simple, easy concept finding domain and range from a graph. So our next concept, our next example is we're asked to find the y-intercepts. This is one, once again, we're going to estimate, and then we're going to find it algebraically. So we're given the equation f of x is equal to x squared minus 4x plus 4. Okay, and right there you should have a hint about where your y-intercept is. If you remember how our equations typically break down when we deal with just looking at the equation, 9 times out of 10, the constant is the y-intercept, right? And we know that from Algebra 2, the work that we did. But they want us to estimate it graphically. So we're going to find our y-axis, and we can go 1, 2, 3. It looks like it crosses at 4, the y value of 4. So we're going to say that 4 is our y-intercept. Now we have to check it algebraically. Okay, and the way that we check it algebraically, once again, I've written down the equation, is we want to find what f of 0 is. Okay, so if we're f of 0, we're going to plug a 0 in for each area we see x. And then we're going to solve it. So PEMDAS makes me start with my exponents. 0 squared is 0. Minus 4 times 0, anything that's multiplied against a 0 is 0. Constant stays as a plus 4. So 0 minus 0 plus 4 gives you the value of 4 for f of 0. Okay, but you can do it pretty quick and pretty easy if you remember how polynomial functions work. Because 9 times out of 10, the constant at the end of the equation or the end of the function turns out to be your y-intercept. Come on, mouse. So this is their process of estimating it graphically. So f of x intersects the y-axis at approximately 0.4. So the y-intercept is about 4. Solve algebraically. Once again, we're going to plug in 0 for each occasion that we see x. And you can see once all the arithmetic and multiplication is done, we end up with the value of 4. That proves conclusively that for this function, 0.4 is our y-intercept. Okay, here's one's a little bit different. It says use the graph of the function g of x, which is equal to x plus 2 minus 3 to approximate its y-intercept. Then find the y-intercept algebraically. So this is one of those special occasions where the constant is not the y-intercept. So I have g of x, which is equal to the absolute value of x plus 2 minus 3. Okay, and the first thing that we're going to do is we're going to analyze it graphically. So we'll follow our y-axis until we meet. Looks like it meets right about 1 unit down. So we can say that our y-intercept is at 0, -1. But then to be sure that we are correct, we have to plug it in. Okay? So we need to find g of 0 is equal to the absolute value of 0 plus 2 minus 3. We treat the absolute value like parentheses. We're going to handle any operation that is inside the absolute value first. So 0 plus 2 gives me the absolute value of 2, which is just 2. And then my constant drops all the way down. 2 minus 3 simplify this down to a -1. So g of 0 is equal to a -1. That's what we estimated using the graph. Now we've proven that algebraically. So we can say without a doubt that our y-intercept is -1. This is a good one. So one more time for good measure. It says use the graph of the function to approximate its y-intercept, then find the y-intercept algebraically. So once again, we're going to go and follow our y-axis up, and it looks like it crosses 2 units above the origin, which would be at the y value of 2. Okay, but once again, we have to plug it in. And if you analyze this equation, if we were to plug in a 0 here, 0 to the 4th is going to be 0, minus 3 times the 0 squared, which is still going to be 0. So this is one of those special polynomial functions where the constant is our y-intercept. So our answer should be D. Once again, to check it algebraically, we plug in 0 to every occurrence that we have x. Follow PEMDAS, so you take care of your exponents first. So you'd have 0 to the 4th minus 3 times whatever 0 squared is. So that would be 0 minus 0 plus 2 yields us 2 as the answer. Okay. So you can see y-intercept, domain, and range are pretty simple, pretty easy. Looking at the graph, and the y-intercept is probably one of the easiest things to find algebraically because, like I said, it's most of the time your constants. But here, we're asked to find the zeros or we're asked to find the roots. Okay? This, when we're talking about doing it algebraically, it can be very difficult because we have multitude of ways. Okay, you might end up using the quadratic formula. Okay, if you have a parabola, you'll probably end up factoring. Okay, there's a multitude of ways, and I can't give you just a blanket list because it kind of depends on the problems that you have. So, but you have the algebra wherewithal to handle all of them. Shouldn't be that big of a deal. So we're using the graph of f of x, which is equal to x cubed minus x to approximate its zeros, then find its zeros algebraically. So now we're talking x-intercepts. So it looks like I cross at -1, the x value -1, the x value of 0, and the x value of 1. Okay, so I think I have 3 x-intercepts. They're at -1, 0, and 1. And I think those are going to work. Okay, probably the first way that you would think about solving this to prove it algebraically is to just plug these in, right? If we can find if f of x is equal to x squared or x cubed minus x, I can find f of -1, f of 0, and f of 1. Okay, and that can work, and I can do it pretty simply. So -1 cubed minus -1. So -1 cubed is -1 times -1, which is a positive 1, times another -1, which gives me -1. And then minus a -1 turns into a +1 to give me 0. So that one would check out. Okay, f of 0 would be 0 cubed minus 0. Once again, 0 times itself is going to be 0 minus 0 is equal to 0. So that one checks out. Then I can find f of 1 by plugging 1 into my equation, taking 1 cubed. 1 cubed is 1 minus 1 is equal to 0 as well. So I could solve that by plugging them in. Once again, it's not necessarily the most efficient method that I'd have. Okay, one of the other ways is I could look at trying to factor this. Okay, I've already proved that they're all algebraically roots, but if I wanted to go down the factor route, it's a binomial term, and I'm looking to factor out the greatest common factor between x cubed and a negative x. So that being said, that would be just x. So if I factor out an x here, x cubed divided by x gives me x squared, and x divided by x gives me 1. Okay, so now after I've factored out the greatest common factor, I have x times the quantity of x squared minus 1. Then once again, this could be factored even farther. This is what's known as a difference of squares. Okay, its factored form is going to be two binomial terms. It's going to be the term a plus b and a minus b. It's called the difference of squares. So its true factored form, all said and done, okay, and this would all have to be set equal to 0 because I'm trying to figure out when my y value is 0, because that's the only way I have an x-intercept. Okay, the zero product property states that I can break that for this to equal 0, one or all of these must equal 0 since they're multiplied. Anything multiplied against itself or anything multiplied against 0 is going to be 0. So the first one makes it very easy. X is equal to 0. That gives us that. Our second one, x plus 1, we set that equal to 0 and solve for x. I'd subtract 1 from each side, and I'd get that x is equal to negative 1, which is one of the graphic points that I estimated. And then my third one, x minus 1, if I set that equal to 0, and then I isolate my variable by adding 1 to each side, I get x is equal to 1. So looking at my values, I have x is equal to 0, that equals 0. X is equal to a negative 1 would give me a 0, and x is equal to 1, which are the three that I estimated. So just there, you have two different ways to solve it algebraically. This is one because it is factored. Okay. So the book's method is they're going to walk you through factoring it. So first we estimated it graphically. There's a lot of work in there, so I'll show you the graph once again. We determined that, hey, it looks like there's a 0 at negative 1, looks like there's a 0 at 0, and it looks like there's a 0 at 1. So those are the points that we're going to work from as our estimates. Appear to be about negative 1, 0, and 1. And then they ask us to solve it algebraically. Okay. And they've set x cubed minus x is equal to 0. You can see on the right-hand side it says let f of x equal 0. That's because the only way we're going to touch the x-axis is if our y value is 0. So then they factor it to x times x squared minus 1. Okay, and then this is them factoring out this binomial, which I said once again is a difference of squares. Anytime we have a perfect square in the term A and a perfect square in the term B, our factors are going to be the roots or the square root of both of those. So x squared is x squared. Then they set them equal to 0. Okay, and that's from the zero product property. You can see that 1's already given. And then for x minus 1, which is equal to 0, and x plus 1 is equal to 0, they just solved. Okay, so here, they plus 1 from this side to bring it here to get x equals 1. And then on this one, they subtracted 1 from this side to bring it over here to get x is equal to -1. So the zeros of f are 0, 1, and -1. And we've proved that algebraically. We were able to estimate it graphically. So we're perfect right now. So the answer we would give is -1, 0, and 1. Okay, this one's a little bit harder. Okay, it says use the graph of f of x, which is equal to x plus 4 minus 3 to approximate its 0, and then find its zeros algebraically. Okay. So if we're using our graph, we want to follow our x-axis to the right, and it looks like it crosses at 1, 2, 3, 1, 2, 3, 4, possibly the 5th unit, because they kind of cut us off here. It's not a very good graph. I'd love them to extend that a little bit, but I'm thinking it's going to be about 5. Okay, so once again, I can do a ton of things. I could plug in f of 5 in there, and then I could solve it that way. So if my f of 5, that's going to be equal to the square root of 5 plus 4 minus 3. Once again, we're going to treat the radical. We're going to treat the radical like parentheses, and we're going to do those operations first. So I've written in and I plugged in 5 for f, or 5 for x. So since these are under the radicals, I treat them like parentheses. I have to take care of those first. So that's the square root of 9 minus 3. Square root of 9 is 3. So 3 minus 3, which is equal to 0. So that would say that f of 5 is equal to 0 there. Okay, and I could make that happen. Or the other way I could do it is for f of x, I plugged in 0 here, and I said the square root of x plus 4 minus 3, and then I tried to solve for x. Trying to solve for the x value when my function is equal to 0. So I plus 3 from both sides. Okay, so that would give me 3 is equal to the square root of x plus 4. In order to get rid of my square root, if I square both sides, 3 squared is equal to 9, which is equal to x plus 4 now. Now if I subtract 4 from both sides, I have 5 is equal to x. So, and that's what I guessed. That's what my multiplication, me plugging x5 in, because that's the one that I estimated. That's the one that it looks like graphically it makes sense to plug that one in first. Or I can set it up and solve it. And from there, my internet connection is unstable. That's not a good sign. And you can see the book agrees with me. 5 is our correct answer for our root of the equation. Okay, here we're talking symmetry. So it'll be the last couple things that they ask us. I'm going to give you a couple minutes to write it down while I'm talking about it. You can also see it out of the McGraw-Hill book. I posted this slideshow as a PDF to the lecture activity, but you can also see it if you choose to go to your McGraw-Hill book. It is on page 16 of the McGraw-Hill book. Once again, the easier way is probably just looking at the PDF or writing it down. So this first one says the graph of the relation is symmetric with respect to the x-axis if and only if for every point xy on the graph, the point x negative y is on the graph. Okay, so here's xy where they're both positive. Here's x negative y when our y value is negative. And since we have the same x value, that would cause us to use the x-axis as gives you x value symmetry. So replacing y with negative y produces an equivalent equation, or that it's on the graph. The next one, the graph of the relation is symmetric with respect to the y-axis if and only if, for every point xy on the graph, the point negative xy is also on the graph. So here's xy, here's negative xy, and you can see that they both fall onto our graph. So replacing x with a negative x produces an equivalent equation. And then the graph of the relation is symmetric with respect to the origin if and only if for every point xy on the graph, the point negative x, negative y is also on the graph. So here's negative x, negative y, here's point xy, and you can see that they've rotated it because it's point symmetry. They've rotated it 180 degrees. This one, with respect to the y-axis, is line symmetry. With respect to the x-axis is also line symmetry. So line symmetry, point symmetry. Okay, I'll give you a couple minutes to write that down. We'll look at a couple of them, and then I'll turn you loose on your homework. Oh, I got to talk about even odd functions too. Dang it. All right. So here we are testing for symmetry. It says use the graph of the equation y is equal to x squared plus 2 to test the symmetry with respect to the x, the y, and the x-axis, the y-axis, and the origin. Support your answer numerically, then confirm algebraically. Okay, so the first thing we want to do is we want to look at which one makes sense. So this one, it's not going to have x-axis symmetry or origin symmetry because we never go beneath the x-axis. It's one of the requirements for symmetry about the origin. We have to have a negative y value. Or symmetry about the x-axis, we have to end up as a negative y value. Okay, so just right there, we can tell that this one isn't symmetrical about the x-axis. It isn't going to be symmetrical about the y-axis, or symmetrical about the origin, but there's a possibility that it is symmetrical about the y-axis. Okay, and remember that what we have to do is we have to pick certain points, and if we plug in one x value, and then we plug in the negative of that same x value, we should get the same y value if it has origin symmetry. So I'm going to start to build a table here. And I'm going to try to pick nice, easy points for me to work with. So I have f of x, which is equal to x squared plus 2. So I'm going to try to find what's f of 1. And then I'm also going to find what's f of negative 1. Okay, those are going to be my first two, because if those match up, chances are I probably have y-axis symmetry. I might plug in another point just to be 100% sure. So for f of 1, I'm plugging in 1 for each x value. I get 1 squared, which is 1 plus 2, which is equal to 3. So f of 1 is equal to 3. So now if we look at f of negative 1, negative 1 squared is 1 plus 2, which is equal to 3. And you can see my points, if I were to list them in ordered pair, would be 1, 3, and negative 1, 3. This corresponds to y-axis symmetry. It says for any xy value, that if we were to plug in the negative of that x value, we should get the same y value. Okay, because I'm skeptical, I don't really know if I'm true or not, I'm going to take it even farther, and I'm going to plug in f of 2 and f of negative 2, just to be sure. So for f of 2, it's 2 squared plus 2. 2 squared is 4 plus 2 is equal to 6. And then for f of negative 2, it would be negative 2 squared, which is 4 plus 2, which is also equal to 6. If I list them out as ordered pairs, I have 2, 6, and negative 2, 6. Okay, so this to me seems as if, and I could carry it on, I would believe that 2 points is more than enough, but I could carry it on to 3, 5, 6 points, depending upon how unsure I am. This one is pretty obvious because one, the graph, and the second way, and the way that my points and my tests have turned out. So I think it has y-axis symmetry. Okay, so it seems to represent it graphically. And then they support numerically. You can see they carried it out to a negative 3. I just stopped at negative 2. So when you plugged in negative 3, you got 11. But then when you plugged in 3, you got 11. When we plugged in negative 2, we got 6. When we plugged in 2, we got 6. When we plugged in negative 1, we got 3. When we plugged in 1, we got 3. So this supports that we have y-axis symmetry. Okay, so here we have another one. It says use the graph of the equation xy is equal to a negative 6 to test for symmetry with respect to the x-axis, y-axis, and the origin. Support your answer numerically. Okay, so once again, we're going to graphically use it to make sure that we're not going to be wasting our time. So if we look at the y-axis, if I were to just flip this straight across, you can see that I would create almost the same graph, but the function wouldn't overlap on top of ourselves. Okay, that's also the same thing with the x-axis. So this one doesn't have any line symmetry. Okay, but it could possibly have symmetry about the origin or point symmetry. Remember, for point symmetry, it says for each xy, the points negative x, negative y should also be on that function or be the same. Okay, so this one's going to have a little bit of a change because symmetry about the origin as x, y, which gets transformed into negative x, negative y, or the opposite. Okay, so for the first thing I have to do is I've been given the equation xy is equal to a negative 6. I got to get it in terms of y and x, so I'm going to divide both sides by x. And the real equation I'm working with is y is equal to negative 6 over x. Okay, so that's my equation. I'm going to rewrite it to give myself a little bit of room. And then I'm going to pick x values that are quick, easy, and simple. So I'm going to use 1, 1 and negative 1, 2 and negative 2, 3 and negative 3. Those being with 6, they should work out very simply. Okay, I know this says y, but this could also be f of x. It's just function notation. So what's f of 1, f of negative 1, f of 2, f of negative 2 first. Okay, So f of 1 is equal to a negative 6 over 1, which is equal to a negative 6. So ordered pair would be 1, negative 6. Negative 1 would be equal to negative 6 divided by negative 1, which would be 6, or negative 1, 6. And if you're looking, this shows point symmetry about the origin just with these two given points. So when you're thinking about negative x, negative y, you want to think about taking the opposite. So when I plugged in a positive 1, I got a negative 6. But when I plugged in a negative 1, I got a positive 6. These are both opposites of each other. Negative 6 is the opposite of 6. 1 is the opposite of negative 1. So my first points check out. Okay, if I plug in 2, I'm going to get negative 6 over 2, which is equal to a negative 3, which gives me 2, negative 3. And then negative 2, negative 6 divided by negative 2, which is equal to 3. Negative 2, 3. So once again, these are opposites. 2 is the opposite of negative 2. Negative 3 is the opposite of 3. So those check out. That shows point symmetry about the origin. We analyze graphically. It appears that for every point x, y, there is a point negative x, negative y. Then we built our table. So once again, they did negative 3 and 3. So when they plugged in negative 3, they got a positive 2. When they plugged in 3, they got a negative 2. These are opposites. And then negative 2, 3, 2, negative 3, once again, they're opposites. Negative 1, 6, 1, negative 6, once again, opposites. Since they are exact opposites of each other, that supports the conjecture that we have point symmetry with respect to the origin, and that would be odd. I have to get off. I have to go into work. Emma, school is your job. What are you doing? What are you doing? Okay. So use the graph of the equation y equals negative x cubed to test for symmetry with respect to the x-axis, the y-axis. So I'm just about done. This is the last thing that I'm going to do and talk about even odd functions. Then you guys are going to do your homework. And then just if you have to get off, just understand you have homework tonight. Okay, you do. It's about 20 problems, and you'll see the activity on Seesaw. So once again, on this question, I've given y is equal to a negative x cubed, and I want to test for symmetry. Graphically, I'm going to eliminate some. So y-axis symmetry is not there because if I were to flip this graph over the y-axis, this part would come here, this part would come here, they wouldn't overlap. X-axis is the same thing. So I think that this has symmetry about the origin. Okay, and we want to support this. So I'm going to plug in the points 1 and negative 1. If I plug in negative 1 cubed is negative 1. And then it's an opposite, so it's negative 1, 1, which falls right here. And then if I plug in 1 cubed is 1, and then I have to take the negative, which is right there. So this would be symmetric with respect to the origin. Okay, and as promised, the last thing that I have is even odd functions. Okay, functions that are symmetric with respect to the y-axis are called even functions. Okay, so for every x in the domain of f, if f of negative x is equal to f of x, it's symmetric about the y-axis, and that is an even function. And then you have odd functions, which are symmetric with respect to the origin. Okay, in the situation that these do not fall, or you don't have symmetry about the origin or symmetry about the y-axis, it is not an even function and it is not an odd function. It's a mandatory requirement. So the example they have here says x squared minus 4x plus 4 under graphing calculator, then determine if it is even, odd, or neither. So could it be even? Does it look like it has symmetry about the y-axis? Graphically, I'm going to say no. No, not at all. Okay. Then could it be symmetry about the origin, which would make it an odd function? Graphically, once again, I'm going to say no. Okay, if I were to plug points in, if I were to plug in a 1 and a negative 1, if I plugged in 1, I'd have 1 squared, which is 1, minus 4, which is negative 3, plus 4, which was 1. So that point's going to be right here. So I'd have 1, 3 as my answer. And then if I plugged in negative 1 squared is 1, minus 4 times the quantity of negative 1, which would be 5, plus 4, that's all the way up here at 9. Okay, so f of 1 was 3, f of negative 1 is 9. This does not have any symmetry. I mean, it has line symmetry through probably x is equal to 3, but it's not an even or an odd function, so I'm going to say neither. Okay, the key things is when you're talking about even odd, it just has to be symmetric about the y-axis. It could be symmetric at a different part of the xy plane, but if it's not about the y-axis, it is not an even function. Same thing with your point symmetry. It can have point symmetry at a different position on the xy coordinate plane, but if it's not at the origin, it is not an odd function. Okay, so I just assigned your homework. I'll leave it spinning just in case if you guys have a couple questions. Your homework today, it is page 19, 2 through 40 evens, and it's to be completed by Tuesday, tomorrow at midnight. Once again, if you don't have a graphing calculator, you need to graph or you need to download an app called Calculator X. Okay, and I'll pull mine up. I don't know how I'm going to do this. If you look at my phone, you can see this little application here, Calculator X. When you open it up, what? Is that better? You can see it opens up into a graphing calculator. Okay, very, very useful for you, especially for problems 34 through 40. Okay, almost mandatory to have it. You can also use Desmos graphing online. And those are for the last problems because they give you some pretty difficult equations to work with. You have like square root of x plus 6, absolute value of 8 minus 2x. Ooh, and then you have a reciprocal function of x plus 4 divided by x minus 2. Yeah, Claire, you need to turn in your notes. Always. We got to make sure you guys are paying attention. There's an activity on Seesaw for it. Without further ado, you're off working on your homework. I'm going to leave the Zoom call spin.